Hello, everyone, and welcome to Global Hack Week. I hope you've been having a good Global Hack Week so far. We're back today with the second session of streams on data structures and algorithms in Python. This time we're back for the 102 series. If you were here for last month's Global Hack Week, I ran a similar stream series on data structures and algorithms, but it was a little bit more basic of technology or basic of concepts. Today and tomorrow, we're going to be diving into a little bit more intermediate of concepts and improving our data structures and algorithm skills a little bit further. So welcome to Global Hack Week, February 2026. We're doing a bunch of streams related to data this week. We're getting towards the end, but I hope you've been having a good Global Hack Week so far. Let me know in the comments if you have enjoyed any of your previous streams, if you have any favorites so far, or if this is your first stream of Global Hack Week so far. Also, before we dive into any more content, I'd like to introduce myself. If you're new here to Global Hack Week, or you haven't been on any of my particular streams before, my name is Gabriella. I'm a coach here at Major League Hacking, also known as MLH. As you can see in my background, it says MLH a bunch of times, and you may hear myself or other coaches or other MLHers on stream refer to Major League Hacking as MLH. That's our fun little acronym for Major League Hacking. Outside of my work at MLH, I'm also a full-time software engineer. And my fun fact for today is that I just returned from a trip to Mexico City. I had a great time. I absolutely loved getting to see Mexico City. It was my first time there. I had so much fun eating a bunch of delicious food, seeing so much cool art, and just walking around the city. It was a great time. And also highly recommend if you are looking to escape cold weather to go to a warm location like Mexico City for vacation. But now that I've introduced myself, we can dive a little bit more into the stream logistics for today's Global Hack Week session. If you've been on one of my streams before, you'll know that I typically have a bunch of short links for the content as well as the code of whatever we are covering on today's series. So as you can see here, there's two links up on the screen. The one on the left, bit.ly/DSA 102 slides. That's the link for the slides that you see up here. So if you want to go back and reference any of the materials, whether it be an explanation or you just want to find the master the master doc with all the links to everything, then you can go there. In addition, for today's session, we're going to be going through a lot of LeetCode style / data structures and algorithm style problems, and you can access our code after the stream at DSA-102-code. I'll upload everything we work through, and my typical style for this stream and problem solving in general is to comment everything, so you can kind of see the comments and the thought process that we went through, just in case you aren't able to follow along the entire time, or just want to go back and reference things because if you ran into internet issues, you joined a little bit late, or you missed a session because you had to study or had other conflicting things or time differences, whatever. You can access the code there later. All right, looks like we have a few people saying hello, good morning. Oh, we have someone tuning in from India where it's 5:30 in the morning. Thanks for tuning in. I appreciate the dedication to learn a little bit about data structures and algorithms. It's currently 7 here in New York, so not too late, but a little bit after work and school hours. A little bit less people, I guess, because it's a little bit later or earlier in the day, depending on where you are. But glad to have you all here, and we can go through some data structures and algorithms for the close to end of Global Hack Week. Also, as a little bit of a shout out, before I go through what data structures and algorithms are and talking through kind of what to expect for the problem solving of this stream series. As you can see on the left, there is a link for registering your attendance with Major League Hacking. If you haven't done that already, please click on that link and register your attendance with Major League Hacking. That makes you eligible for any swag drops or achievements related to Global Hack Week and your participation in it. I'll drop that in the chat as well. So you're able to see that for a little bit after when I am talking about everything else that's on the screen, but make sure that you're registering your attendance. And I also dropped this in the Discord, but I just want to make sure that everyone is getting their attendance points. Okay. Apologies, just need some water. So as far as what data structures and algorithms are, if you're new here or just like new to data structures and algorithms in general, DSA stands for Data Structures and Algorithms, like I've said a few times. What a data structure is, it's a defined way to organize, store, and manipulate data in the memory of the program. These are things like list or arrays, depending on the language you're in, a string, a dictionary, a linked list, a hash map, and more data structures. Those are the, I don't know, a few that came off the top of my head. We're going to be talking about linked lists today and a little bit of work with list as well, just like plain list, as we do a little bit of review from last session or last stream session. As far as what an algorithm is a step-by-step programmatic rule for solving a problem. So we'll learn some algorithms throughout the course of the stream series, and these will be common approaches for how to solve problems, whether it be in your normal work as a software engineer in general, or specifically for solving technical interview problems. Sometimes you'll also have these algorithms as you'll be quizzed on these algorithms when you're in a computer science course. There are many courses on data structures and algorithms, but also it's just a useful way of thinking about coding and syntax in general to make you into a better engineer and a more efficient engineer. Yeah, and as far as why you want to even learn this stuff, if you are just tuning in or just a little bit unsure, these are pretty valuable skills like across the board. I touched on this a little bit, but these are primarily what are used to quiz potential software engineers when you're interviewing for a job. So these are very useful skills if you are in university and you're trying to get an internship or a full-time job. If you are currently a software engineer and maybe a little bit rusty on the different data structures, you don't use a certain algorithm in your day-to-day work, brushing up on the different kinds will be very helpful if you're trying to find a new job. And also just brushing up on data structures and algorithms in general is a good practice or good thing to do if you just want to be a more efficient and better engineer after you've landed that job or just working on projects. I've noticed that like when I was in university or like afterwards when I've been prepping for interviews at different points, that when I'm doing these problems and reviewing these concepts more, it does help me out like in my day-to-day at work as well, because I'm able to think about more efficient ways to solve problems. I'm thinking about the memory. I'm thinking about the time and space complexity of different applications and different ways to solve problems, so that like if you're thinking about these things and know different algorithms will make you into a better and more efficient engineer like once you actually land that job. So good to know across the board. So that is kind of like the overview of what data structures and algorithms are. As always, if you have any questions, feel free to drop them in the chat. I want to make sure that I'm making sense to y'all and you're able to get something out of these streams. I know that we try to cover a lot of material in them, but I want to make sure that anyone's questions are answered. And if you notice, like I have made a syntax error or some other thing on screen, definitely shout that out as well. That has happened on more than one occasion, and it's always good to have multiple sets of eyes on these things as well. We have a question. Will we get the slides on which you are teaching us DSA? Yes, I have a short link that was on an earlier slide that links to all of these. They're not a ton. I tend to spend the majority of the time actually coding and working through these problems with y'all. But I will share that at the end of the stream as well, and I'll put it in the Discord after the fact, so you can access the slides as well as the code we work on. All right, so as far as our agenda, so I told you all what data structures and algorithms are. Here's what this stream session will be on. If you were with us for Data Structures 101, I went into some basics on binary search. I did some basics on strings, and we did a lot of work with dictionaries and lists. We're going to be doing a little bit more complex binary search problems, as well as a little bit of a review. I know it's been a month, so some of y'all might be rusty if you tuned in last time, or if this is your first time joining us for a data structures stream, then you might need to learn some of the material from the get-go. We're also going to go into linked list a little bit. Linked list are not one of my favorite data structures, but something you need to know regardless. A common joke is that the first thing you need to learn for a software engineering interview is how to reverse a linked list. It's a pretty basic coding interview question, one that I don't know if it's asked as often as the jokes make it seem, but I did have it as a question a few times when I was interviewing for internships in university. So it's good to know, as well as the more complicated questions as well. That will be our first session. And we'll also have concept reviews on binary search as an algorithm and linked list as a data structure. I'll point you to some more in-depth resources as well if you want to dive more into the concepts behind that and need to review that a little bit more. And tomorrow we're going to be diving into trees. We'll do a little bit of review to kind of solidify that learning on linked list. And then we'll go into that data structure and going into some tree problems as well. Trees are kind of built upon the linked list data structure. They're different, but somewhat similar data structures. So after we've gone through and learned some more about linked list and solved some problems with that, we can continue to build on that. And those are also pretty frequently seen in software engineering interviews. So that is what we'll be covering. I'm also curious just to know who is tuning in. If you could answer 2 questions in the chat, I'm going to put this up as a banner as well. But I'm curious, how many of y'all have worked with Python in the past is the first question. And the second question is, have you done LeetCode or solved like data structures and algorithms questions before? So if you could just answer those questions, maybe in your comment, put like 1, yes, 2, no, if you know Python but haven't done LeetCode problems before. Just I'm a little bit curious. I'm gonna put this up on the screen, and I'll wait for those to come in. Okay, we have some 1s. Does this mean that you have worked with Python? I want to make sure that I understand you. Look like we have someone who has not learned any data structures but's working in machine learning. Okay, awesome. So you know Python, I'm assuming, if you're working in machine learning. We have a lot of people who have worked with Python. Awesome. Okay, we have some people who know Python and done some basic data structures. The reason I'm asking this is I just want to know how much to do review and how much to explain a little bit more in depth versus if y'all were all like old pros at Python and also have done lots of LeetCode problems, then we can just kind of dive straight in and use a little bit less explanation. All right, so it looks like we have a pretty solid mix. So it looks like the majority of y'all are familiar with Python, so that's good. I won't have to explain, excuse me, as much of the syntax and conceptual stuff, but we can just dive more into the data structures and algorithms and actually solving those problems. Awesome. So we can move on to some conceptual explanation of binary search as an algorithm, and then I'll dive into linked list as an explanation before we actually get started coding. And as always, drop any questions you have in the chat. All right, so now we can actually get started with learning and some data structures now that we have all the housekeeping out of the way. So binary search is an algorithm. It's typically used in a list or an array, depending on the language you're in. List and array is just kind of the same name, or different names for the same thing. Y'all are familiar with Python, so you know that it is just a collection of a bunch of different information. It can be numbers, it can be strings. You can have 2D lists or arrays. But a binary search is a more efficient way to create a searching algorithm to find information within your list or array. And how you do that is you're cutting the time complexity of your searching algorithm in half of just going through a normal for loop. For loop is a very inefficient way of searching because you have to go through and look at every single item in that array. But in this one, you're going to use 2 pointers. And these are 2 values that are essentially going to be at the beginning and the end of your list. So you have pointer 1 is going to be at index 0 to start with, and pointer 2 will be at the end of the list. These are called the start and end pointers. And then you're also going to have a middle value. And this will be determined by finding the average of the start and the end pointer. And what you're going to do with this middle value is you're going to compare it to whatever you're searching for. And if the value you're searching for is greater than the middle value, you'll set your start or first pointer equal to the indices of the middle value plus 1, because you know that if it's greater than that. And it's, I guess, like as a kind of side note, you're assuming that the list is sorted in ascending order. Then you can continue searching and you'll cut your search time in half because you've axed off looking through all the items that are from, I don't know, index 2 through index 4 as like an example. And similarly, if you're looking for if you're looking for a value and it's less than the middle value, then you'll move your end pointer to the middle value, the middle indices subtracted by 1. So you're kind of cutting the sub list that you're looking at to search it. And this just like will make it so that you have less iterations to search through your list. So rather than in, I guess, the example image we have from Geeks for Geeks here, this is the length of this list is 10. So instead of having the for loop iterate through something 10 times over, you're only going to be searching for it 3 times in this particular example before you find your item. And while it may not seem like a huge drastic difference from 10 to 3, that scales, and especially with how large applications are today and how much data they process, cutting that down by 60% is a massive difference. And you'll want to, and as that scales, it'll make it a better application and one that'll, like, the difference between it running properly, completing whatever search you need to run, and it not executing properly, or it failing because it's taking too much time to execute. So that is what binary search is. I think we're going to continue and just talk through linked lists after this versus diving into problems straight away. And then after I explain what linked lists are very quickly, we can dive into actually coding. If you have questions and you want to look back at the reference image, let me know. I might do that as I'm explaining things, but I think that'll be a little bit easier. Excuse me, with my setup. All right. So as far as what linked lists are, these are a linear data structure that allow for a more efficient insertion and deletion compared to a list and array. And this is because of how everything is linked. So a linked list, if you're unaware, is made up of nodes that are linked together via their values. These are most typically linked via their next values. There is something called a doubly linked list where it has previous values as well. I don't think we're going to get into solving any of those problems in today's session. Maybe we'll do some tomorrow if we have some extra time. But typically, for the most part, these are linked together via their next values. As you can see here on the screen, we have a few different nodes here. So every node is labeled A, B, C, D, like in this diagram. The first node right here is referred to as the head. So whenever you get a linked list, you can start traversing through it by the head. And each node has both the data and the next value at a minimum. Like I said, Some of them have a previous and doubly linked list. But in this one, for the example, it only has the data and the next value. So A, B, C, or D is the data in each node. And you can access the data in each of these nodes by referring to the particular, like the node that you're at. And that'll be dot value instead of dot data. It's a little bit, I guess this diagram isn't maybe the best worded, but it is like the data that's within the node. And you just refer to it as the value when you're pulling it out. And then if you want to find the next node in a linked list, you're going to do head.next. And if you want to traverse through it, but you're not just going to get this exact node unless you're at the end. What you're going to get, because of how a linked list is you're going to get this will be equal to the next head if you're traversing, or if you're just selecting like head.next, it will come here. And you'll be able to access the data pretty easily if you do head.next.value, and you'll get B right here. But if you just type something out like return or print head.next, you're not just going to get B. You're going to get B and then the node pointing to node C, and then the node C pointing to node D, and then you'll finally get to the end of the linked list of node D pointing to null. So with linked lists, you have to be a little bit more particular about how you're accessing things. But because they are structured, it is a little bit easier with insertion and deletion, and a little like memory and efficiency wise. All right. And also some, I guess, more information on linked list. The first node is referred to as a head. I think I talked about that in the beginning, but if you were unaware, this is called the head, and you can also reassign the head as you're traversing through the linked list. That's like the pretty standard way of doing it. And then the next value right here is referred to as the pointer. In other data types, sometimes a pointer or whatever is directing you to the next element, whether it be a node or something else, will be referred to as something different. But in this case, it's referred to as a pointer. So you have your data, your pointer. These are also called values. Values and pointers for like what it's actually called and how you are interacting with it in the actual code. Data and next for what the diagram says. And the last pointer will always point to null or none. It won't just like kind of drop off and have like the data. It has to have a next value, even if the next value is null or none. It won't just be empty. All right. So that is a little bit of an explanation of linked list. And now we're going to dive into doing practice problems because I want to have as much time to talk through this, to debug, and to answer things. We're going to start with linked lists and then go into a little bit more complex of binary search problems. We did a few binary search problems in the previous stream session. I just want to build upon that knowledge because binary search as an algorithm is a basis for other searching algorithms and is used pretty widely in interviews. All right, so we'll click here. And I'm going to, refresh my LeetCode page. I'll send this in the chat as well. As a reminder, if you are tuning in a little bit late, you weren't here for the entirety of the stream, I will have the code linked for all of these problems that we solved together. After the stream, you'll be able to access it. I'll push it to a GitHub repository. But if you want to solve it along with me and test out your own test cases, I will send the link to this problem in the chat. But all of these problems are on the PowerPoint that you will have access to after the stream is over. All right, so I think that maybe as a little bit of a review, instead of just diving into linked list cycle, we can maybe do reversing a linked list just so we have a little bit of a refresher for everyone who is maybe new to tuning in, or if you were a little bit rusty and you haven't done any LeetCode since we last talked. All right, so sorry, I'm just getting that leak code problem. And this, as I talked about, like a little bit jokingly earlier, is a very common problem to solve in interviews. But because it's the most basic linked list problem, I think that this is what we're going to solve first. And then we can dive into a little bit more next ones. Okay. So we'll have this problem. Perfect. Okay. So as you can see here, we have our reverse linked list problem, and we have a diagram. This one is a little bit more clear of like what we want to actually accomplish versus the Geeks for Geeks image we had in the PowerPoint. That was more conceptual. This is what we're talking about, what we're actually going to do. And when I'm solving these problems, I typically like to do a 1-sentence summary of the problem we're solving, and then we go into the actual steps we're going to take, written out, sometimes pseudocoded a little bit, and what we actually need to output. This way I can kind of talk through the thought process. And then if there's anything that doesn't make sense, or we run into an edge case as I'm talking it out, it's a little bit easier to course correct than if we had already started coding. And also, as a pro tip, this is a great way to practice on your own, whether it be with you and a rubber duck, your teddy bear, or you and a friend studying for interviews or tests. This might not be something that your professor is looking for, but when you're interviewing for different technical positions, this is something they definitely are looking for, is to see your thought process, because they don't just want to have a software engineer who can memorize a bunch of leak code problems or memorize like the patterns of a few things. They want someone who can receive feedback, someone who can problem solve in real time, because you won't be able to just memorize the most common solutions when you're building an application. You need to actually absorb the information and be able to make changes based off of new information and actually problem solve. What they're looking for is someone who can think, can communicate well, and is good at problem solving, versus someone who can just solve leak code problems. These are just kind of a problem solving means test versus the accuracy of them 100%. So now that we have that out of the way and kind of an explanation of why you want to make sure you're talking through everything and why I will be very specific about it, let's dive into this one as a review. All right, so for reversing a linked list, we're given the head of a singly linked list. We need to reverse the list and then return the reverse list. Okay, so in this one, what we need to do, we need to take the head of a linked list, reverse the nose, and then return it. And then what we're going to return is the reversed linked list. And as far as what we're going, like the actual steps that we're going to take, is we're going to traverse, I need to spell this properly, traverse through linked list. And then what we need to do is we need to swap our values of the next. Swap the next values. So we want this value right now, the node of 1, its next value is 2. We want the next value of 1 to be null, and we want the next value of 2 to be 1 instead of 3. Swap the next values, and then just kind of continue. So this is a pretty basic problem, so this verbiage is pretty basic as far as what we're doing, but I think now we can dive into actually coding all this out. So, and a little bit of kind of talking through this a little bit more, how I'm going to go through and actually traverse the linked list so we're able to return everything properly, is you want to make a copy of the head so we're able to actually access it later. So we're going to create cur equal to head. So what this is doing is it's creating a copy of our linked list at the value current. And this is so we're able to actually traverse through this linked list and swap those values and then still return the new head of our value. And then in addition to that, we're going to want to create a placeholder value for previous. And we're going to set that to none initially. And why we need this placeholder value for previous is because we want to hold the previous node so that we don't just lose that when we change the linkage. Because here, as you can see, when we're switching the next value of 1 from 2 to null, we don't just want to lose the one node once we get rid of that linkage. We want to still have that as in a value so that we can add the next value of 2 to be equal to the 1 node. So that placeholder is going to be equal to none initially. So we're able to link it to our 1 value at the beginning of our linked list. But we will change and update that to be the current node that we're on. So we're able to have access to that and swap those nodes a little bit easier. All right, so now that we've done our basic placeholder declaration, we need to actually traverse through our linked list. And we do this pretty simply. It's just going to be while current. And this is a basic while loop. It's just going to iterate through our linked list while current exists. And once we get to the end of traversing our linked list, current will no longer exist, which is why we needed to make a copy of the head. So we didn't just lose the end. We didn't lose the head and have to return null when we had actually successfully removed that. So then while we're traversing our linked list, we want to hold a placeholder value for our next so we can begin to swap. So I'm just going to have it be equal to nxt because if we do next spelled out fully, we're going to run into some issues with syntax. If you have something that is the same verbiage, it sometimes will give you issues in Python and lots of other languages. But in our next value, we're going to set that equal to current.next. So this will be right now equal to the node of 2. So we have access to that 2 value. And now we're going to begin actually swapping them. So then we're going to set our current.next value. And we're going to set that equal to previous. So what we've done here is we've put our 2 node into a placeholder. And we've set the next value of 1 to be equal to previous. And as we've established up here, previous is none. So that has successfully swapped this arrow to be pointing this way rather than towards the 2. So it'll be pointing towards none or null. As you can see in this diagram, it's not actually pointing to that because there's no extra node, but that's kind of implied as far as how the diagram goes. I just want to make sure I'm explaining it explicitly so you're able to understand. And then after we have moved our next value, we need to put our current value into our previous placeholder so that as we continue to iterate, we have that stored. So we're going to do that just by updating our previous placeholder right here. And we're going to be setting that equal to current because our current value is still the 1 node that has been set to. The value of this 1 node is 1, and the next value of the node of this 1 node is null. And then after we've done that, we can continue to iterate. So we're going to continue to iterate or traverse the linked list. And we can do that by saying current is equal to current.next or not. It'll be equal to next. I made a little slip up there. Typically, when you're traversing through a linked list, you'll do current.next explicitly. But because we've set our current.next to previous, that would not actually traverse. So I caught myself in real time there. But we're going to set it equal to next, which is equal to the old value of current.next. And this will successfully traverse through our linked list, and it will swap those next values so that we have our 1 is now the tail instead of the head. And now all we have left to do is actually return our linked list. And we can do this by returning the previous value because the previous value will be where our head is stored. once we traverse through the entirety of this linked list. So we'll do return previous, and now we can run. All right, it looks like all of our test cases have been accepted. For those of you who are new to LeetCode or new to data structures and algorithms in general, I'll spend a minute kind of explaining what this interface is now that we've solved our first problem so that y'all are able to understand how this works if you start practicing on your own. There are multiple test cases that are kind of like a preliminary test. I like to think of this as when you're working on a project and you have a few test cases that you're kind of manually testing, such as like print this value or return this value, and you do it for a couple times of calling your function. So you're making sure that there's a basic foundational like functioning function. That's kind of a funny way to put it, functioning function. But that's kind of how I like to think of these. You can also add your own unique test cases. So in this, I'll do 1, 2, 3, 4, all 5, just as like a new test. And here we have it's passing. But then what you'll want to do is you'll want to hit submit. And I like to think of this as when you are actually running legitimate tests in your code. So you're able to see it passes. Oh, it doesn't look like it fully executed. Oh, it just is over here. Oops. Okay, we'll have this. Here we go. Okay, this is a little bit more full, and now you can see it. So the submissions, like I was saying earlier, these are when you're like running legitimate tests on your code that are checking for multiple test cases, testing for edge cases, and also because you're running it with large enough data sets that if it isn't very time efficient, it's going to crash. So this is just testing it at a larger scale. Typically, there's a few 100 test cases. This is a more simple problem. So there's only 28 test cases in this case, but it'll show you how your runtime and memory stacks up against other people who have submitted them. And a cool feature that I like on LeetCode as well is you can see, like in this case, our memory suffered because our runtime was so high, and say we wanted to increase, like better our runtime. And we can see there's a decent number of people who used 14.2 megabytes of memory instead of our 14.5. We can go here and see what they did differently. And it looks like they declared a next value preemptively, but it's mostly the same. Sometimes it's like something very simple, or just like the submission time is what is determining the percentage. But other times you might have a very memory or time inefficient problem, and clicking in that, like learning what other people did, can be a very good learning experience as far as how you can improve and what types of things would improve similar problems for lists, linked lists, or whatever type of algorithm you're working on. Also, as kind of like an aside, typically you want to find a good balance of your runtime and memory. In this case, like this is an optimal solution, but other times you might want to like sacrifice a little bit of your runtime so you have a better memory. So maybe it would be 85%, so you can get your memory to beat 50% of it, so it's a little bit more evened out. But typically you're going to have one that is a little bit ahead just because of how you choose to execute your code. So yeah. That is our first problem. So now that we have successfully reversed a linked list, now it's time to move on to a little bit more complicated of a problem. We're going to do a list linked cycle, which builds upon what we just did, but is a little bit more complex than just reversing it. We defined the actual cycle. Does the reversal of the linked list, what we just did here, make sense to everyone? If you have questions, definitely drop them in the chat. I want to make sure this makes sense, but if you weren't able to completely follow along, again, the code will be up after the fact. Okay, so now we have linked list cycle. Apologies, get a little parched when I talk for a few hours at a time on these things. So linked list cycle is where we're given the head, which is the head of a linked list. We need to determine if this linked list has a cycle in it. And it looks like in this picture, a cycle is determined by the next value pointing to a different node within the linked list. And I'm assuming if it's just kind of like a normal linked list, what we saw last time, that's not a cycle. Okay. Oh, and also as like a PSA, this is the problem, that we're working on right now. If you want to go to that link and solve it along with me and run your own test cases. But it's this link. I'll leave it up on screen while I'm talking through this. So you can access that if you want. So if there is a cycle in a linked list, if there is a node in the list that can be reached, again, by continuously following the next pointer. Additionally, POS is used to denote the index of the node that the tail's next pointer is connected to. Note that POS is not passed as a perimeter. Okay, so we're given, okay, it's within the input, but not passed as a perimeter. I'm very curious. If it's not being given, I'm curious if we're going to receive this. It's like worded a little bit confusingly. Oh, okay. Would it be something like has cycle? Huh. Wonder if it would be like head.pos. No. Okay. We're going to just ignore that for right now. I think that we can solve this on our own. They worded that a bit confusingly. But as far as what we need to actually get out of this, we need to return true if there is a cycle in the linked list. And otherwise, we need to return false if we have not found a cycle. So let's look at a few of the test cases. This is the first one. There's a cycle because -4 points to the indices or place of node 2. Here, this is just like a circle basically, and this is a one node linked list, so it obviously can't be a cycle because there's only one. And the next of that node is pointing to null, so there's no cycle. Okay, so this is a little explanation of linked list cycle. Now let's go through the notes and kind of get a grasp on what we're looking for and what we want to do. Okay, so we are given a linked, yes, we should specify head of a linked list. What we need to return, true or false. We're not returning anything in the actual linked list. And then after we are given the head of the linked list, what we need to do is figure out if there is a cycle. So as far as my instincts for solving the linked list cycle, my instincts for this would be if we can figure out essentially as we're traversing this, if the node is being repeated, because in this, I think we want to keep a record of all of these, and then we can maybe compare that to see if we're seeing the same thing twice. As I'm saying that out loud, I think that's probably the brute force solution. But it's what's first coming to mind. I think we could also do maybe like I guess we could do like a fast point, like a pointer situation with a fast pointer and a slow pointer. I guess I'll talk through both and we'll see what makes more sense. So we'll have record of previous nodes if head.next in previous nodes will return true. And then if we get to the end of our node, or not, if we get to the end of our linked list, sorry, we return false, because if there is an end that we can actually get to, then we will be like, we'll know that it's a normal linked list and there's no cycle. Okay. And then for fast and slow pointers, essentially like what I think that the logic here would be is we can have a pointer that's just looking at like head.next, and then we can have one that's like fast that's looking at head.next.next. And we can eventually see if those two are lining up and we're seeing like we're seeing a like fast and slow being equal to each other. I guess the like downside of that is that I see like I will have to iterate through a few times for it to catch up, but I think it might still be more efficient than having to store everything like I was talking about in a brute force solution. So fast and slow pointers, head.next versus head.next. If the value, or not if the values, if fast and slow, because we don't want to have a situation where we have a linked list where like the node value is 2 in multiple places versus if we just find the actual cycle. So we want to make sure that we're finding the actual nodes, not just the value, are equal. Then return true. And then I guess similarly, if we can finish the loop, then return false. So here we'll have our brute force, and here we'll have more optimal. I don't know if this is the optimal solution, but it's definitely more optimal. Okay, I think this makes sense so far. Now we can actually get started coding and see is it actually working. All right, so in this we want to make 2 copies of this because we want to have a copy for both fast and slow. The reason why I'm going to get a copy of them is sort of just like having it be equal to like fast is like equal to head.next from the get-go, and slow is equal to head.next, is because we want to have a copy of the entirety of the linked list, not just from that value on. Because if we wanted to detect a pointer, we don't want to, once it like kind of loops around in the cycle, it to not have, in the case of fast, the first 2 values, the first 2 nodes in our linked list, in the case of slow, to not have that. So we're just going to make 2 generic copies of our linked list. And then after that, we can start with our while loop. So we'll do, let's see, while fast exists, and we'll do and fast.next. And this is essentially just checking to see if fast has a next value, we can continue. Because if fast does not have a next value, we know that there is no cycle, so that we can return false, because we need to make sure that there is a next value. We can actually check to see if there's a cycle within. All right, so now that we're looping through it, we similarly need to reassign / iterate through our different pointer values. And we're going to set that equal to, let's see, fast.next. And then for slow, we're just going to do slow.next. And then we're doing this by slow and fast instead of just head.next, because we're going to take the individual copies of both just to make it easier. And if we were doing this and manipulating the values for both slow and fast, it might get a little bit messy and we might chop something off by accident. So make sure that that is all in alignment. And then, like we said, if the nodes are equal, then we can return true. Because we're checking for the nodes, it's a pretty simple statement. If fast is equal to slow, we can return true. And we're doing it very simply, not something like fast.val and slow.val, because we want to make sure the entire node is equal, because we need to have that next value to determine the linked list cycle. All right, we're going to return true, and we're going to get rid of these explanation dummy values. And then we also need to have outside the loop a return false. And this is just the catch-all. If our while loop executes, then we're going to get the entirety. We're going to get those cases where there is no cycle, so that while loop is able to exit. We're going to have a return value for that as well. All right, so I think this is the crux of it. I'm going to run the basic test case and see if those pass. All right, some basic test case are passed. I'm going to try with another one just because I'm curious. Let's see. Okay. We'll do I'm curious if we're not putting the actual values, what's going to happen here. Like the next values for nodes. All right. Nice. I guess because the way we're inputting it isn't in list link format, it's just a normal list. It's assuming that the next values are there. All right. So now we can submit this and have it tested against all of the more major test cases. I don't know why it continues to show up on that side of my screen in the tiniest possible format. But we can hopefully drag it over so we can actually see this thing. All right. So it's accepted. All 29 of our test cases are passed. This also seems like a low number of like extreme test cases, but I'm assuming it's just maybe lower for linked lists. Maybe there's less things that can go wrong or you need to test for in arrays that I have kind of forgotten about since I haven't worked with linked list a little bit. But it looks like we have a pretty time efficient solution. It's beating 92 of the other solutions, and the memory has suffered just a little bit because we're only beating 28% of the other respondents. I'm curious to see what these people did. It's only 0.2 millibytes better. I don't know if it's, I think it's maybe megabytes. And then we can see what saved them a little bit of time. Okay. So if head is none or head.next is none, we are returning false. So they're checking to see if the linked list is empty or if the linked list only has a value of 1 immediately before we go through the for loop. And then it's going to just automatically return false. Okay, and then this is curious too. They set fast equal to head.next, and it, I guess, saved them some time. Or maybe this is what's saving them the 0.2 MB. And then similarly, they did while fast.next is not none, so exist. And okay. So making sure that there's like 2 values ahead, and they're checking to see if they're equal, return true, otherwise increment upwards. Okay, overall it's pretty similar. This is achieving essentially the same thing as what we did. This seems to be the only material difference that I think would make a tangible difference in our memory complexity. Okay, that's interesting to know. All right, so nice job, y'all. We're just cruising along. There don't seem to be any questions thus far. Again, reminder, if you have any questions, drop those in the chat. I'm going to give y'all a 1-minute intermission while I go fill up my water to get a little bit more. So we'll be back in one more second. But grab a little bit of water, take a bathroom break, check your code over. But we have a little 1-minute intermission. See y'all in just a bit. There's my audio. We're back. Hope y'all had a chance to grab some water. I just filled up my bottle. We're cruising along. We can get started with our next problem. So we did a little review of our reversal of a linked list. We went through a linked list cycle problem. So now we're going to move on to merging our 2 sorted linked lists. I think this one may be our last linked list of the day. We'll see how quickly we get through it, because I do want to make sure we have some time for our binary search as well. All right, so for this one, we're taking 2 sorted linked lists. So as you can see here, we have a linked list that's made up of 1, 2, 4. It's sorted in ascending order. And then we have another linked list that's sorted also in ascending order of 1, 3, 4. And then we want to merge these 2 lists into a single sorted list. And it should be made by splicing the nodes together of the first 2 lists. And then we need to return the head of the new merged linked list. My question here is, do we want to put it in one of these existing linked lists, or do we want to create a new one? That's what I'm unsure of, but I'm just going to talk through what it's asking and what we're actually going to do here. Okay, so given, do, return. So we're given 2 heads of linked list sorted ascendingly. What we need to do, merge in ascending order. And then we need to return the head of our newly merged ascending linked list. Okay, so as far as the steps, let's talk through those together. So we have our 2 linked lists. Okay, I think what we're going to do is just create a new kind of like dummy value. And when we create that dummy value, we can begin to splice in the nodes versus doing it in an existing list. It doesn't say that it has to be in an existing linked list that's provided. And I think that by creating a dummy will make it a little bit easier for ourselves, so we can just traverse through the 2 and not need to worry about anything else. So I'm going to create a dummy linked list / node to merge our linked lists in. And then we're going to need to traverse through the 2 linked lists. And essentially what we need to check for after that is which values are greater than each other. So we're going to need to access, I guess, compare the values of the current node in each linked list, and then append the lesser one, continue if not equal, because like in this case, we have, so say like we're traversing through the linked list, we start here, 1 is equal to 1. So we'll just, I guess, like append whichever one. I don't really think it matters if it would be the node in the first linked list or the second linked list. And then since they're equal, we can just append both of them and like continue traversing. But once we get here, we'll compare the value of where we're at here, 2 and 3. And because the value of 2 is less than 3, that's the one that'll get appended or merged into our mega linked list. And we'll continue to traverse the first linked list. So it'll be 4, and then this one will still be at 3. And since the value of 3 is less than 4, that one will get merged, and we'll like traverse this one upward. And then as we can see here, these are equal, so they can both get appended. But in the case where I'm curious if it dictates, it doesn't say that both of the linked lists are the same length, I don't think. So we might have an instance where we have a linked list that's a little bit longer. So for example, linked list 1 is like a length of 5, and after 4 we had 5 and 6. We would just want to append or merge that towards the end of our linked list. So I think that's why this makes sense. Okay. I got 2 and 2, looking at the diagram to type everything out, but I think that explains it, at least in a way that I understand it. If you have questions, again, drop them. I don't want to make sure anyone's confused, but append the lesser one, continue if not equal, if equal, I'll make this a little bit clearer. If equal, append both values and traverse appended list. This makes more sense here. And then after we've traversed through, because I think our while loop is going to be something to the effect of while there's like a list 1 and a list 2. So once we have exited our traversal while loop, what we essentially want to do is if list 1 or list 2 have remaining values, we just want to merge / append those onto the end of the merge linked list. Okay. And then we'll just here, we're going to return our dummy linked list that everything was getting merged / appended onto. Okay, so that all makes sense. Now we can begin actually typing it out and explaining everything. Or not explaining everything, I just explained everything now, but like typing it out and actually testing it. All right, so we're going to have our dummy value, and we're going to set this equal to just be a normal list node versus a fully fleshed out linked list. And we're going to do this so that we can set the next value equal to whatever node we want to capture, because we want to have it as a linked list and not a just like a normal array. That's why I think the dummy makes sense here. And then I'm also going to make a tail value and set that equal to dummy. And this is just us making a copy of it so that we're able to access that head later when we want to return it. The name is a little bit confusing, but I think because like it is different enough, we'll be able to remember what that is. And we can always change it if it gets to be too confusing. So like I said earlier, we'll have while list 1 and list 2. Let me double check those are the names it's giving us. Yes. While list 1 and list 2, we need to go in and check to see if those values are the same or different. So if list 1 dot value is greater than list 2 dot value, what we're going to do is we're going to go to dummy dot next, and we're going to just append on list 2. Because this is the head, we'll get that value in the next, and as we iterate through it, we'll be able to add on the other values. We don't need to explicitly type it out as much as you might think or I thought when I first started solving linked list problems. Then after we do that, like I said earlier, we want to iterate upon the one we just added. So list 2 will be equal to list 2 dot next. And then if we have essentially anything else, we just want to add it on. So we'll have dummy dot next will be equal to list 1, and then we want to iterate upon them like this so we can actually access those next values. And we also want to make sure that we are iterating the dummy value so that we are not replacing the dummy.next value. We want to iterate on that as well so that we have our values after we add on 1 and 1 pointing onto the next node. So we'll have dummy be equal to dummy.next to iterate upon that. And then after that, when we have successfully traversed through everything, we're just going to check if list 1, then we'll do dummy.next will be equal to list 1. And then we'll have if list 2, dummy.next will be equal to list 2. And then I think after that, we can just return tail.next to get our merged list. And this will essentially just take our copy of the dummy value, and then we can return it from the true head, not the dummy head that we have here. All right, let's test this and see if it's working properly. Awesome. So we have our 3 test cases are working properly. Let's see if all of them are working correctly. I don't know why it keeps popping up here, and I'm finding this very annoying. I don't know if I can fix that later, but all right. So our runtime is beating 21%, and our memory is beating 11%. So this is not great runtime. Not great memory. This is, I guess, just like what came to mind. So I'm gonna click on this to see what had better runtime and see how we can change our code. So they have dummy node. Their tail is just called new. All right. This is basically the same. This is the same. Oh, okay. So then they're for the if statements. I think they probably did what we had done initially too. Having an if statements to see if the well, I guess not entirely, but it was a similar thought process of checking to see if list 1 and list 2 were there. And then appending them on to the new or the dummy value. But what they have done is they've just set their next value of new, which is dummy, to be equal to list 1 or list 2. And I guess it saved enough to go from a 3 ms of runtime to 0. That's very curious. I want to see if we can do that here and have it work. List 1 or list 2. If that saves us that much runtime, that would be great. Awesome. Made our runtime actually go down. So I guess it wasn't that. Huh. I guess they're adding everything into new.next instead of dummy. It might just be that LeetCode is being a little finicky with the test cases. Let me try this one more time. Bring it back up to our initial. Oh, now we're up to 1 millisecond of runtime. So as I had said earlier, LeetCode is a little finicky. So I guess it was just who was submitting at that time. Our memory is pretty good. We're beating 80%, but our time complexity is taking a little bit of a hit for the benefit of this. But I'd say this is a pretty good solution. Yeah. Any questions? Definitely drop them in the chat. All right. Awesome. Okay. So it looks like we have about 45 minutes left. So I think that we're going to go through and reorder a list, and then we're going to do some binary search problems because we do still have like a lot of time left. Okay. So let's go to reordering our list. We're just cruising along here. All right. Okay. We're gonna get rid of my previous attempts at this, and then we can get started. So as an explanation, let's go through and read out what I have. Also, we're kind of moving up the ranks. I don't know if you noticed, but all of the problems we had solved earlier were denoted as easy. Where's the description? Here it is. They were denoted as easy. All of LeetCode problems are marked or denoted as easy, medium, hard. Those are kind of just to see how difficult they are. They're not always the most accurate thing, but this one will be a little bit more challenging and is, I guess, more in line with getting a little bit more challenging, a little bit more intermediate. The majority of interview problems I found, at least in early levels, the first few years you're a software engineer, tend to be at the medium level. Whereas when you kind of progress in your career, you might get to hard level problems in addition to systems design stuff. And then if you're interviewing for an internship, typically you'll see problems that are marked as an easy or a medium, depending on how competitive the company is or just like what type of role you're applying for. But yeah, typically if you're just getting started in this, pretty new in your career, easies and mediums are pretty good to stick to. And you can go for the occasional hard if you'd like to challenge yourself. But also, sometimes problems are marked as easy when they're pretty difficult, and there's a lot of really easy mediums, so it's not an exact science. All right, anyways, little tangent over. We're given the head of a singly linked list. Head of linked list. We need to reorder it to be in the following form. We cannot modify the values in the list nodes. Only the nodes themselves can be changed. This is to prevent us from taking, essentially to get all the values in like a normal list or something, and then go through and change them. So let me see what the formula is. So we want it to go from L0 to L1 to L0 to Ln to L1 to Ln minus 1 to L2 to Ln minus 2. Okay, so we want to kind of flip-flop them. So we have here an example that makes a little bit more sense. I'm a very visual person. So we're swapping the last value to be the second value. And then we want our, I guess that's the only change that's taking place in this particular one. But if it was to be a longer linked list, we would then go on to the fourth value, and we take the second to last value and swap it to be the fourth value. In this case, we don't need to actually do anything for that because it will already be the last value after we've swapped them or inserted it. Yeah, so right here we can see the last value is taken to the second value, and then we have our second to last value is taken. Oh no, I'm curious. Okay. So we have our last value is taken to the second value, and then the third value is taken to the end. Oh, I guess I see that because we're going to want to have, this will be what? L3, or no, it'll be L2 because it's 0 indices as well. Okay, that makes sense. Interesting. Okay. So we've talked that through. You're going to figure it out. Now let's get through actually making some steps. So we're given the head of the linked list. What we need to do is rearrange the nodes, not just the values, just to make sure we have this little condition in our heads. We don't want to do any brute force or squeezing past the rules. And then what we want to return is our modified / reordered list. Okay. So how are we actually going to get there? So I think this is going to be we're going to want to iterate through everything and swap the second value in the last until we meet the middle, I think. I think that's what we're going to want to do. So swap last value with index 1 / second value until you reach the middle. And in this case, we need to iterate through our linked list to actually find like the length of it so we can find the middle. To find length and therefore middle value. Yeah, okay. And then we'll return after that. That makes sense. And then we can just go through and return. Okay. I think this one I'm going to figure out as I start coding. So I'm not going to stop talking through and explaining it. And we can hopefully just get started coding. Okay. So yeah. Okay. So we'll have our okay. So while just have copy here be equal to head. While copy, we'll do length of linked list equal to 0. While copy okay, yeah, I guess we'll do it like that. We'll do length of linked list. We're going to add 1 by 1, and we'll have copy. Excuse me. Sorry, I just had to cough for a second there. All right, and then our copy will be equal to copy.next. We can print copy and then copy divided by 2 to see if this is working. Oh no, it's going to be, I forgot the name of it. Oops. So it's getting 4 for the length and then 2 for the middle. Okay. And then while index is less than middle, we're going to set index equal to 0, and then middle will be equal to length of list, linked list divided by 2. What we're going to do is have we're going to need like some more complex pointers here. I think that instead of doing it this way I think we could figure out eventually, but I do think it is the brute force solution. I think we're going to need some fast and slow pointers instead. Just because like the more I think about it, in this case, we're going to need a faster pointer to actually access the, not just the value, but the actual node of the last item in order for us to swap them. So I think we want to have a swap that is in line with this So we maybe have the fast pointer, the second pointer is at the end, and we can kind of like iterate that upwards until we get to the middle. And then we'll have it, it'll be completely swapped then. Okay. This is starting to make a little bit more sense. So let me just make those slow and fast pointers, and I'll comment this out just so y'all can kind of see my thought process as well after the fact. So let's make a slow and a fast pointer, and let's set them equal to head and head dot next for right now. It's not the end, but we can't just access it like we do in like a normal list like this. We can't do that in a linked list. So after we've established that, so let's leap through to make sure that we find, I guess let's loop through so we can find our, like the places for our actual pointers. And then we can go through and begin swapping after we've done that. So while we have a fast, and we have a fast dot next, we're going to go through and set slow equal to slow dot next, and fast will be equal to head dot next dot next. So this is going to arrange our pointers where we want them to be, because we want to get our pointer to have one in the second value at index 1 and one to be at the very end. And then we can begin to mess with those as we swap the values. Okay, so once that while loop is executed, because we've gotten to the end of our linked list, then we can move on and start to do our second traversal / pass through. So we want to set our next set of pointers to be a little bit more explicit. So we'll have our second, and this is just going to be where our, like at the second item. So this is just going to be equal to slow dot next, and then we will have our previous value, and this is going to be equal to slow dot next equal to none. So this is taking the slow dot next value and setting the pointer equal to none, so that we can have it be the last value here when we're swapping it before we alter that. All right, so now time for our second pass through / traversal. So while we have a second value, so essentially while we have a value here that is closer or like before our middle versus actually literally the second value in our linked list, we're going to go through and we're going to update or swap those two. So we're going to need some temporary values like when we reversed our linked list from the get-go. So we'll just have a temporary value right here, and that's just going to hold our second dot next. So this will be the node that is pointing to 3, because we don't want it to point to 3 when we swap it with the last value. We want it to point to null, but we don't want to lose this node entirely. And then after we set up that placeholder, we can start actually adjusting the node values. So then we'll have our second dot previous. Like I said, some lists are linked, or not some lists are linked. Some linked lists are dually linked, and you can always play with the previous value. So like in this case, we're doing it manually, but in other cases, this would be a built-in function. So this will be, we don't want to do it quite like this. We want to have our second dot next equal to previous. So in this case, we'll have this 2 node be set equal to previous, which is slow dot next equal to none. So it'll be that node, and the next value will be set equal to none. But as we update that previous value, it won't always be equal to none. And then because we want our second value to next be the previous because we want to continue to traverse through this linked list. This next placeholder of previous, or not next, but this placeholder of previous will get updated to the node of second. And then for second, we need to iterate through again. And we're going to do temporary because this is where the true next value of this lives, so we can actually traverse through our linked list. All right, so our second pass is done, and we've done the majority of the swaps. But now what we need to do is we need to go through our linked list one more time, just so we can arrange it in a way where it will print properly. So we're going to create a few more placeholders before we go through our last our like last traversal. Sorry, I'm getting a little bit sleepy. It's not too late here in New York, but you get a little brain fuzzy after you do leak code for a while. Okay, so let's set up our placeholders of first and second and set those equal to head as well as previous. And then while we have our second value, we're going to go through a second traversal, and we're going to set some placeholder values so we can hold on to our temporary next values because we don't want to lose those. So we'll have our first dot next and our second dot next stored here so we don't lose them for when we want to do some arranging in a bit. And then our first dot next will be equal to our second. So here our final swapping will happen with our items, and then we'll do the same thing for same thing, but a similar thing for our second value, and that will be equal to temporary one, which will be first dot next. I think that, oh, I see what I did here. We're going to need to have the next value, both of these be equal to our placeholders, but we're not going to actually be iterating up, and then we can start iterating right here. First and second is going to be equal to our temporary placeholders. All right, let's test this. Let's see if it works. It mostly makes sense to me. None type has no attribute next. Slow dot next. Huh. Oh, I see what's happening here. This will be fast.next.next because we're iterating upon the base case and not our actual value, I think. Yeah. Okay. It's always the small stuff. So if you missed that, um, I, instead of on line 32, putting fast is equal to fast.next.next for iterating with our pointers, I had it equal to head, so it wasn't updating the value properly. It was iterating upon the head, not the fast value. Okay, so let's submit this and see how it goes. Again, onto the side. Not my favorite, but we make do. All right. Okay. So runtime, it's beating like 40, like almost 50%. Memory, it's beating 34. I'm curious to see what the difference is. I think it's, again, it's just checking to see if it's an empty linked list ahead of time. We have, oh, they did more. I guess this is also 3 passes. I think this is maybe let's test this and see if this is what the runtime, the memory difference is for this. We'll do this first thing. Yeah, okay. That increased our runtime, but not our memory. Let's see what the difference is. Our runtime went down a little bit. Our memory went down slightly, but not significantly. But I guess it does save a little bit of time. So that's useful. I'm not going to dwell on this too long. It's solved, and I want to do at least a binary search problem before our time's up. We have about 15, 20 minutes left. I want to make sure that we get in some binary search time. So back to the presentation. We'll do searching a 2D matrix, or I think what we'll do, since there's not that many tree problems, is I'm going to do the basic binary search problem. And then if we have time, we can dive into searching a 2D matrix. But we can do a little bit of binary search in tomorrow's session as well. If you aren't aware, you haven't been following all of the, if you haven't been following the schedule for Global Hack Week, we're also having a part 2 to data structures and algorithms in Python 102 tomorrow, same time, 7 p.m. Eastern. They'll have the conversion to local time on the website when you click on it or when you look at the actual event, you'll be able to see what time and your local time zone it is, and you can also add everything to your calendar. But 7 to 9 p.m. Eastern again tomorrow, and we'll be doing some binary search as well as some tree problems as well. Okay. So let's do a basic binary search as a little bit of a memory refresher. Binary search, at least for me, are much easier than linked list problems. Linked list problems I kind of see as a necessary evil. But binary search is a little bit more fun, entertaining for me. All right. I realize that I haven't been pasting all the links in the chat as we have been going along for all of these, but I'll definitely, everything will be on the slide and you'll be able to access the links to these after the fact. But for binary search, this is the problem. So for Python 3, student normal Python. Okay. So binary search, like I said earlier, you essentially have 2 pointers. You find the average of the 2 pointers to find the middle indices. And then based off that middle indices, you'll compare that to whatever value you're looking for. And that will cut the search time in half. So that's just a basic problem we're solving here. And that's the algorithm that we're going to use for searching a 2D matrix in our next problem. All right, so we're given, let's see, let's make a comment right here. So we are given list with integers sorted in ascending order and a target int. What we need to do, create 2 pointers, create and calculate middle value. And then what we're going to do is we're going to compare middle value in our list to target value. If they are equal, we can just return, what are we returning? We're returning the index. The index. Otherwise, we'll have an elif statement to see middle is less than target. We're going to need to set our P1 equal to middle plus 1. And then otherwise, we've determined that the middle value is greater than target. And then we'll need to set our P2 equal to middle subtracted by 1. And yeah, and then we'll have a if loop finishes, return -1. That's a bit of an edge case, but this is just essentially if it doesn't exist within the list. All right, so that's the basics of binary search. Now we can go through and actually start coding. So we'll create P1 will be equal to 0. P2 is going to be equal to the length of, what is it? Nums is what our list is called, subtracted by 1, because as y'all know, you're familiar with Python, everything is 0 indexed. So the last value will be not 10. If there's 10 items, it'll be 9. And then we're going to go into our loop. So while P1 is less than P2, we'll calculate our middle value, which will be P1 plus P2, and then we're going to divide that by 2. Why do the 2 slashes instead of just 1? Y'all are familiar with Python, but if you're not familiar with this particular operand, this essentially rounds it, so we're not getting like 1.5 because there isn't going to be a 1.5 indices. We want to make sure that we're being like more precise with our middle value. In this case, it doesn't necessarily matter if it rounds up or down because we just want to cut the time in half and get to an O log n runtime complexity. In other cases, you might want to be more careful with rounding up or down. But that's just what we're choosing here. And then we're going to see if nums at middle is equal to our target, then we can just return middle. And then otherwise, like I said, middle, I guess we'll have nums at middle is less than target. P1 is equal to middle subtracted by, what is that? No, if it's okay, it's less than, it'll be addition. And then our else statement where P2 will be equal to middle subtracted by 1. It's going to decrement to get our to the window within where our numbers will be. And then otherwise we can return -1. because the loop has executed. Return outside function. Oh, I want this to be in line with this. Oh, is it because I see what's going on here? I changed it to normal Python, so the function is not within the class to run the code. Okay, so we need our search function. I guess we needed Python 3, whatever. Okay, I think the indentation is right here. Let's try this again. Unindent. Oh, okay, this is annoying. Do we need to have it be? No. These are online. Okay. Okay, this is my least favorite part of doing stuff like this. Getting the indent to match properly. Okay, hopefully this will work. There we go. Okay, the indent is normal. Benefit of Python is you don't need to use semicolons. Downside is you have to have everything properly indented. So, pros and cons. Oh no, wrong answer. Output is 0. Okay, so we need to have an edge case for if our problem doesn't have enough to be and have binary search actually be implemented. So we're just going to need to check to see. Maybe we do, instead of that, instead of checking ahead of time, instead of it just being if P1 is less than P2, if they're equal to each other, because that way then both P1 and P2's values can be aligned, and then this could execute properly instead of making a whole other if statement. But I'm not sure if that's correct. Let's test it out. All right, that was the case. So what I just did was the while loop will execute if P1 and P2 are equal to each other. So in the case of like where we have, make a new test case. It's just 5. What it's going to do is here, oh, I forgot the closing thing. I'm not being super careful here. Here we go. Okay, so in this case, the index at 0 will be P1, and then also the length of this is 1. So subtract by that will be 0 as well. So while P2 and P2 are equal to 0, we can see that the middle of that will also be 0. Then we can return that proper integer value, and we don't need to make a bunch of extra if statements to get that to properly execute. All right, so we have about 8 minutes left. I'm not going to start searching a 2D matrix just yet. It's a medium problem. It's a binary search problem. It's a little bit more advanced than what we just did. Obviously, binary search is like the most simple of the binary search problems. I want to make sure we have enough time to properly go through and explain all of that. And I'll go through a little bit of housekeeping, answer any questions if they exist. And I can share the registration and feedback links as well. So these are all the LeetCode links to the problems we have solved and will solve. So you'll have access to those after I share the short link. But now it's time for any questions, and I'll talk through these links right here. So the first link, bit.ly/DSA 101 slides, is where all the slides are for these. The DSA 101 code is the GitHub repository where I'm going to push all the code that we worked on today, so you can go through and like look at the solutions, the notes I talked through after the fact. And then also, I'm going to call this out, put this up on screen so that y'all can see this. We at Major League Hacking always want to make sure we're doing our best and continuing to improve. So we have this feedback form. We would love if you could fill that out. If you have anything you really enjoyed about today's Global Hack Week stream or anything you think could have gone better, feel free to drop that in the feedback link. And also I'll put the short link to the slides and the code in Discord after the fact. But I do want to call back to, here it is. Here as well is our sign-in link. I'm going to bring that up on the screen one more time. If you joined late or you didn't get a chance to do this earlier, please fill out your attendance for the session so you can get credit for it with Major League Hacking for any potential swag drops or just recognition for your achievements and learning throughout this week. I want to make sure that we're getting that, and also we can see what types of sessions y'all are interested in. Yeah. Any questions? How did it go today? Do you feel like you have a better understanding of data structures and algorithms? Do you have questions? Is your brain a little bit fried? Whoever was tuning in from 5:30 a.m. in India, are you a little sleepy? Are you feeling energized? I enjoyed this. It's always fun to solve puzzles with y'all. And I'll be back again tomorrow at 7 Eastern. Yes. And a question. I did not see this earlier. My apologies. A pointer is a non-primitive data type that stores addresses. Yeah, that's correct. It's essentially just pointing to the address or the location of the next node in this linked list. All right. Thank y'all as well. I had fun solving some LeetCode problems with you. See you tomorrow at 7 Eastern. And thanks for tuning in. I'll see y'all tomorrow. Bye-bye. Happy Global Hack Week.